Hello students, this is Mr. Wilsey, and in this video we're going to be looking at objective number 13 in Algebra 1, which is titled Relations and Functions. You would have gotten proficient/advanced if you could translate among various representations of relations, including a set of ordered pairs, a mapping diagram, and a graph, and then also if you could identify the domain and range of a relation and determine whether or not it is a function. And then finally, if you could evaluate functions using function notation. Now, let's look at question 13.1. Consider the relation -3, 2, 4, 1, -2, 3, 3, 1, and 0, 5. Okay? So this relation is given to us as a set of ordered pairs. Now, in order to identify the domain of a set of ordered pairs, we look at the x values. So the x values of this set of ordered pairs are -3, 4, -2, 3, and 0. So we're going to put all of those numbers into a set of brackets. So -3 is in the domain, 4 is in the domain, -2 is in the domain, +3 is in the domain, and 0. Now, in order to identify the range from a set of ordered pairs, we look at the y values, which are the second coordinates in the ordered pairs. So 2, 1, 3, 1 again, and 5. So in order to write out the range, we will put those numbers into a set of brackets. 2, 1, 3. 1 is repeated, so we only include it once, and then 5. Now it doesn't matter if these are in order from least to greatest or not, although it does help if they are. Now, let's draw a mapping diagram for this relation. That means that we are going to draw a oval or a box for the domain, and then another one for the range. I'm color coding this, but it's not necessary to. Color coding it just for your benefit. Now, inside of this oval, we're going to have all of the numbers in the domain. -3, 4, -2, and again, it doesn't matter if these are in order or not. And then we're going to have all the numbers in the range, 2, 1, 3, and 5. Again, we do not repeat the 1. The 1 is in the range only one time. Okay, you don't list it multiple times. Now, a mapping diagram needs three things. It needs a domain, it needs a range, and then it needs a way to pair numbers in the domain with numbers in the range. And the way that we indicate that is with arrows. So -3 is paired up with 2. So I'm going to draw an arrow going from -3 to 2. A fancy way of saying that is that -3 is mapped to 2. -3 is mapped to 2. 4 is paired with 1. Draw an arrow. -2 is paired with 3. +3 is paired with 1 again, so now I'm going to have an arrow that kind of crosses over here. So +3 is paired with +1, and then 0 is paired with 5. So that is my mapping diagram. Now, part D, let's graph this relation. So we're going to graph these ordered pairs up here. -3, 2, so left 3, up 2. Right 4, up 1. Right 4, up 1. Remember, these are x values, these are y values. -2, 3 means left 2, up 3. Over 3, up 1, over 3, up 1. And then over 0, up 5. So, here's a graphical representation of the relation. Now, it is not appropriate to connect these with lines. Okay? Because if you did connect them with lines, that would indicate that all of the numbers, all of the ordered pairs on that line are also in this relation. But this relation only consists of those 5 ordered pairs. So dots at the location of those ordered pairs is all we need to graph, all we can graph. Now, part E. Is the relation a function? Explain how you know. So in order to determine if this relation is a function, we can look at it 3 different ways. If we looked at just the set of ordered pairs, in order to determine if this relation is a function, we would ask ourselves, are any of the x values repeated? Well, no. None of the x values are repeated. That means that the relation is a function. So, yes, it is a function. And the way that we know that, we can say because A, no x values are repeated. Now, we could also tell that it is a function by looking at the mapping diagram. Notice that there is only one line coming from each number in the domain. That means that each number in the domain is mapped to exactly one number in the range. Okay? So another way that we could say that we know it is a function is by saying each domain value in the mapping diagram has only one arrow coming from it. And then how could we tell that it's a function from the graph? Well, this is where the vertical line test comes into play. If we imagine a vertical line, let me see if I'm looking around me for something vertical. Here we go, this could work. If we sweep out a vertical line, does that vertical line intersect the relation more than one place? Well, no, it intersects it here once, 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 and once. So, this means that our relation passes the vertical line test. And that's how we can tell that the relation is a function just based on the graph, because it passes the vertical line test. Okay? So here's 3 different ways to express how we know that this relation is a function. Now, let's move on to question 13.2. Consider the relation given by the mapping diagram below. So in this case, I give you the mapping diagram, and I'm going to ask you again for the domain, the range, the set of ordered pairs, and then I'm going to ask you if the relation is a function. So, let's first of all identify what the domain is. The domain is going to be this box over on the left. And you can tell because there's an arrow pointing to the values in the range, but there is no arrow pointing to the values in the domain. That means that, well, you see the arrowhead here? That means that values in the domain are mapped to the values in the range. Okay, so domain's on the left, range is on the right in this case. Usually this will be the case. Domain's on the left, range is on the right. So the domain of this relation is going to be all of the numbers in that box. So -3 to 5. The range is going to be all of the numbers in that box. -4, -2, 0, 1, and 5. Now let's write this relation as a set of ordered pairs. Well, let's see. We know that the first x value that we have is -3. -3, oops, I need to write this in brackets and in parentheses. So -3 comma what? Well, -3 is mapped to 4. I'm sorry, -3 is mapped to -4. -3 is also mapped to 0. So -3 comma 0. Now let's look at 2. 2 is mapped to -2. Now 5 is mapped to 1, and 5 is also mapped to 5. So, this relation, just like the last one, consists of 5 ordered pairs. Now let's ask ourselves, is the relation a function? Well, look at the x values from the ordered pairs. Are any of the x values repeated? Well, yes, they are. -3 is repeated. 5 is also repeated. So this is definitely not a function. You can also tell from the mapping diagram, multiple arrows come from -3, and multiple arrows come from 5. And if we had a graph, we would also see that the graph of this relation does not pass the vertical line test. So there's lots of different ways to tell that this relation is not a function. I'm just going to leave that hanging there. So let's move on to 13.3. Draw the graph of a relation that is not a function. Your graph can be made of individual points or can be a smooth curve or line. So in this case, I'm leaving this kind of open-ended. You can just draw any graph that you want. But the graph cannot be a function. So you can do any number of things. You could, I saw some people draw a vertical line, because a vertical line is not a function. In this case, the domain would be -4, and the range would be all real numbers. Okay, so -4 is right there, and the range would be all real numbers if you did a vertical line. Because a vertical line fails the vertical line test. That seems kind of strange that a vertical line would fail the vertical line test, but that just means that our vertical line, which we sweep from left to right, intersects our relation not just multiple times, but an infinite number of times. So it is definitely not a function. So here's just one possible example of a relation that is not a function. You could have drawn any number of other examples too. Yeah. And for the most part, I think you guys did fairly well on this problem. Now let's look at 13.4. Here we're shifting to something a little bit different. We're shifting to function notation. Okay? So what we're asking for is, what is the value of f of 3? Let me say that one more time. What is the value of f of 3? So we pronounce this f of 3 for the function f of x equals 2x plus 7. Well, all this means is replace x with 3 and then simplify. So f of 3 is equal to 2 times 3 plus 7, which is 6 plus 7, which is 13. So f of 3 is 13. We do the same exact thing down here. What is the value of g of -2 for the function g of x equals 3x squared minus 4? So we're going to replace the x wherever we see it over here with -2. So g of -2 is equal to 3 times, now here's the important part, you have to wrap your -2 in parentheses when you square it. Always, always wrap those dangerous negative numbers in parentheses, because this tells you to take -2 and square it. That means you're taking -2 times -2, which is +4. So 3 times +4 minus 4. So 3 times 4 is 12, minus 4 is 8. So g of -2 is 8. Okay, so the important part here, again, was to wrap your negative number in parentheses before you square it. Now, the domain of the function f of x equals -3x minus, oops, I pronounced that wrong. The domain of the function f of x equals -3x minus 3 is, and then we have this set of numbers. What is the range of the function? Write your answer below. All this means is, one by one, take the values of the domain and stick them in for x. So f of -4 is -3 times, in parentheses, -4 minus 3. And this winds up being +12 minus 3 is 9. Okay? And then you do that for -2 and for all of the rest of these numbers. And so I will let you work on that right now while I look at my answer key to see what the actual answers are. Again, you should be copying down everything that I'm doing, especially this work over here. Let me find my answer key for this, because I really don't want to have to do all that work again. I already did it at some point in time. Let's see if I can find it. No, I can't find it. Oh well, we'll just try to do it by head. So that one's going to, so -2 is going to be +6 minus 3 is going to be 3, I believe. And then if you plug in 0, it's going to be -3. You plug in 1.5, that's going to be, let's see, negative 3 times 1.5 is negative 4.5 minus 3 is negative 7.5. Plug in 4, you're going to have negative 12 minus 3 is negative 15. That sounds right. I did that in my head real quick. So you can check my work on that. Now, final problem, 13.7. To the left is a graph of the function h of t, which represents the height of a projectile as a function of time, t. Okay, so we have a projectile, and at 3 seconds, we launch it up into the air. It goes up to a maximum height of 18 meters, and then it falls back down, and then hits the ground again at 9 seconds. So the first question is, what is the domain? And, important, write it as a compound inequality. So, let's look at the domain. The domain is the set of all of the x values, but in this case we have t and h of t. So, what is the x value in this case? What is the independent variable? Time. Time is the independent variable. And it normally always is. Whatever variable is drawn down here on the horizontal axis is generally the independent variable. And this, the set of possible values of the independent variable, is our domain. So our domain starts at 3 and goes to 9. But our domain is not this set. It's not 3, 4, 5, 6, 7, 8, 9. That's not the domain. The domain is all numbers between 3 and 9. All of these numbers. And so the best way to express the fact that the domain includes all numbers between 3 and 9, and not just 3, 4, 5, 6, 7, 8, 9, not just the integers between 3 and 9, the best way to express this is with the compound inequality. So 3, 9, t is in the middle, and then you're going to have inequality signs. Okay, so t can be less than or equal to 9, but t has to be greater than or equal to 3. Okay, you see that? This says that 3 is less than or equal to t. So t can be anything that is greater than 3, if you flip that around, and then also t has to be less than or equal to 9. Okay, so this is a sandwich right here. This is a sandwich. T, the value of t, is sandwiched in between 3 and 9. Now let's do the same exact thing with the range. Write it as a compound inequality. So what's the lowest value of the range? Well, the lowest value is 0. What's the highest value? 18. And again, we want to indicate that all values of h of t, remember h of t just represents a number, and that number has to be between 0 and 18. So 0, 18, h of t is in the middle, and then your inequality signs go like that. So this says that h of t is sandwiched in between 0 and 18. Now, this is an interesting question. What is the value of h of 5? Well, what does that even mean? We're not even given a function rule like we were up here. How in the world can we find what h of 5 is? Well, this just means when t is 5, so t equals 5, let's look over here in the graph. When t is 5, what is the value of h? What is the value of h of t? Well, when t is 5, look up here, boom. H of t is the value on the graph here. So when t is 5, h of t is 16. 16. So what this says is, at 5 seconds, the height of the projectile is 16 meters. Okay, that is it for this objective.